So today class we will discuss about the introduction to the integrated circuits. The integrated circuits when I'm talking about the many transistors on single chip. That is what exactly the meaning of integrated circuits. So now in this particular thing, very large scale integration. So here in the particular thing, okay, when you're talking about integrated circuits, we are considering the many transistor on a single chip. But when you're dealing with the VLSI technology, it is a bucket loads. That means what the plenty of ICs will be available on a single chip. That is what exactly the meaning. So you just imagine the bucket loads means what it's a huge amount. So they are complementary metal oxide semiconductor when you're talking about. Okay, so the advantages are there. Okay, so when you compare with the normal bipolar junction transistors and all, okay, CMOS technology when you're talking about, so CMOS technology will be very fast, very cheap, low power transistor it is going to use. So power consumption is less. It is cheaper in price and it is faster in operation. What else you want? So these particular three advantages made us to think about CMOS technology. So now today at this particular point of day life, how to build your own simple CMOS chip is a challenging task. So here in this particular concept, that CMOS transistor we need to understand. From that particular CMOS transistor construction, working principle and all. So we are going to understand the building logic gates from the transistor. That is a very, very fundamental thing because when you're talking about the any particular circuit, the circuit is made by logic gates. For example, if you take the adder, okay, half adder. So half adder, if you take, will require the one XOR gate, one AND gate. Is a very simple circuit. Also requires two gates. So if you understand how to fabricate, how to build the logic gates of a transistor, after that's the first step. Second step is what? How to configure those built logic gates into the layout. Okay. So in the CMOS chip, okay, CMOS piece or silicon piece, I can say. Okay. Exactly the concept challenging task here. So on the rest of the course, we will discuss about how to build a good CMOS chip. We're going to discuss because there are many aspects how to make it faster, how to make it cheaper, how to make it in a powerless power consumption. So fundamental thing in this particular concept is silicon lattice. So this is the first thing we need to understand. Okay, so because on the silicon only we have constructed all the circuits. So silicon lattice we need to understand. So when talking about the silicon lattice, the transistor are built on a silicon substrate. So silicon is a group 4 material. So it is a chemical composition. So it forms a crystal lattice with bonds to 4 neighbors. You can see that in the diagram. Okay, so here so silicon is a bonding. Okay, so four bonding is present. It forms a crystal lattice with the bonds to 4 neighbors. So one particular thing, if you take, okay, center silicon, if you take, it is having the 4 neighbors to it. That means what? Left one, right one, top one, and bottom one. So if you take the last corner also, it is having the provision, but in this particular diagram, it is not shown. That's all. Okay, so this is the bonding it is having. This is the crystal lattice. So when we are talking about the this particular semiconductor, okay, silicon material. So basically, we know that silicon is a semiconductor material. Okay, so when the silicon is a semiconductor material, we understand that the pure silicon has no free carriers to conduct the current. So if it is a pure form of silicon, what exactly happen? There is no valence electrons, there is no valence holes. So there is no provision. So once there is no provision in that particular thing, okay, pure silicon has no free carriers and conducts very poorly. So now we want to increase the conductivity of the silicon. So when we are thinking of increasing the conductivity of the silicon, we need to add the dopants to increase the conductivity. Okay, so dopants means what? It is a impurities. So we say that impurities. So like arsenium is there, like a boron is there. Okay, so all these things are impurities. When we add this particular impurities to the silicon, so either the holes will the either the number of holes will get increased or number of electrons will get increased. So based on that one, that increase in the charge carriers will makes the current to pass through the silicon. That is what exactly happened. So now silicon is a group 4 element. So we have a provision of adding the impurity with the group 5 or group 3. So in that particular group 5, we have an extra electron. That means what, when we put the dopant, okay, so group 5 means there are 5 electrons. Okay, so that particular material if you take and if you make into the silicon, okay, so what will happen? We'll get an extra electron. So in the group 3, there is a missing electron. That means what? If the group 4 is having 4 electrons, so if the group 3 is having 3 electrons, that means 1 electron is missing. So it will increase the p type. Okay, so that is what exactly the thing which is going to happen. So when you are talking about group 5, it is n types will be added, and when you're talking about group 3, it is p type we are going to consider. So similarly, we can be able to see that in the lattice structure of silicon, we can see that in the center arsenium has been made, and that arsenium it has been indicated as a plus. Okay, so we can get the next hole here. So and here we can see that now when you are adding the boron, so boron the negative sign will come into picture. That means what, one electron is missing. Okay, so that is what exactly the thing which is going to happen. So you know that from the class 1. Okay, so from in the plus 2 also you people have learned that adding the impurity will make the semiconductor, pure form of silicon conductor, to pass the electricity in a faster or larger rate. So now we'll go to the PN junctions. When I'm talking about the PN junction, that is P-type semiconductor and N-type semiconductor is being cascaded together. Okay, so when you cascade the P-type and N-type semiconductor material, so a junction between the P-type and N-type semiconductor which forms the diode. We say that it is a diode. So here, the one of the best thing we can observe is the diode is a unidirectional. So what do you mean by unidirectional? It is the current can flow only in one particular direction. So now you can see in the diagram there is a P-type semiconductor material and it is the N-type semiconductor material. So in the P-type and N-type, so between the, that means what, where the joint is there, no, that is called as what, junction, P-type and N-type. So in the P-type it is anode and N-type it is cathode. Okay, so we say that it is a P-type means what, a anode, and N-type is cathode, we say. So current will pass from P to N. Okay, so we can see that now the symbol of diode is being given. That is like a this is the particular the last below diagram. You can see that is a symbol of a diode. So this particular operation of PN junction is very, very simple. So when you connect the positive voltage to the P type and negative voltage to the N type, the current will start flowing. It is forward biased. And when you reverse the terminals, it is called as what, reverse biased, and the current will not flow. Okay, so that is about the PN junction type. So now we'll go to the NMOS transistor. So you can see the diagram of the NMOS transistor. NMOS transistor, it is having the 4 terminals, that is a gate, source, drain, and the body. So these are the 4 terminals in NMOS transistor that you need to be very much clear about it. The 3 things, that is source, gate, drain, you can see that the terminals, and the body is also one considered as a terminal only, but we'll not use it for our connection purpose. Okay, so the 4 terminals of the NMOS transistor are gate, source, drain, and body. So gate oxide body stacks look like a capacitor. Okay, gate to oxide, oxide to body stack look like a capacitor. So here in this particular thing, if you are understanding, the gate and body are the conductors. Here in this particular structure, entire structure, the gate as well as the body are the conductors. So silicon dioxide, that is SiO2, is a very good insulator. So silicon dioxide is a very good insulator. Okay, that is because silicon dioxide is being used here. Okay, so you can see that between the gate and the body, silicon dioxide has been incorporated. So this particular silicon dioxide is a good insulator. So it is called metal oxide semiconductor. Why it is metal oxide? So it is polysilicon is there upside in the gate, and silicon dioxide is there, okay, below the gate, and between the body and gates, the silicon dioxide is there. So that is why it is called as what? Metal oxide semiconductor. Okay. So it is called as what? Metal oxide semiconductor, because silicon dioxide is an oxide. So metal, where polysilicon is a metal, and the body is silicon, we are going to semiconductor, we say. So body is semiconductor, polysilicon is a metal, and SiO2 is a oxide. That is why it is called as what? Metal oxide semiconductor, metal oxide capacitor, we say, because it is acting as a capacitor. Okay. So even though the gate is no longer made of metal, so even though the gate is no longer made of metal, but still we say that it is a metal oxide. Okay. So now here metal oxides are returning today. That means what? Initial days it was not like that. Okay. So very initial days we are using the metal, but nowadays we started to use something else. So now we can understand that metal gates are returning today. That means what? Instead of polysilicon, we are going to use the metal only. So this is the NMOS. Okay, NMOS semiconductor, NMOS transistor, we can say. So when NMOS means your body will be of P type. NMOS here, the source and drain will be of N plus. The source and drain will be of N plus, and the symbol is written in the right bottom. You can see this is the symbol for NMOS transistor, and this is the diagram, operational diagram for the NMOS transistor. Similarly, when you are talking about the NMOS, when you are talking about PMOS transistor, you can see that. Okay, so here both doping doping and voltages are reversed. Okay, body tied to high voltage. Here gate low transistor is on and gate A transistor is off. That is the operation we're talking about. But we're talking about the construction. You can see that the PMOS, the source and drain are P plus, and the body is N, and the body is N. And between the body and gate, there is a SiO2, that is silicon dioxide. And you can see the symbol of this one. Okay, symbol, you can see this particular PMOS transistor. Thank you for listening.